Okay, continuing on with carboxylic acids, let's learn a little bit about the synthesis and the reactions of carboxylic acids. You will see a lot of it here is going to be a review for you. So let's look at the synthesis, and again, you've done a lot of these before, so hopefully this will go by fast and smoothly. So the first one is oxidation of alkenes and alkynes, and you can take alkenes and use KMnO4 and heat to cleave the double bond here to give two acids. You can do the same thing with alkynes. Alkynes, you can use ozone, or you can also use potassium permanganate. It doesn't matter because alkynes are already more oxidized than alkenes, so either of those reagents will work. Okay, and so again you get two carboxylic acids. So this is also called cleavage of the alkenes and the alkynes, or fragmentation, whatever you want to call that. It's fine. Then you can also oxidize aldehydes and primary alcohols. We've done this before as well. So with the aldehyde, you can use the Tollens reagent, which is the silver oxide, or you can use potassium permanganate, or you can use chromic acid. Any of these is going to work, okay? But remember, with the alcohol, you need to make sure you have a strong oxidizing agent. With aldehydes, it doesn't matter. Because aldehydes will oxidize only to the acid, but it's still good to kind of go ahead and use a strong oxidizing agent, all right? So that will give you carboxylic acid. And then oxidation of alkyl benzenes. You remember that you can degrade the entire alkyl group, whatever is on the benzene ring, using KMnO4. So once you use your potassium permanganate on an alkyl benzene, you will get benzoic acid. You can probably see a pattern over here, and the pattern is that you're using strong oxidizing agents like potassium permanganate in order to make carboxylic acids. So it's a nice thing, okay? It's kind of easy to remember, and by now you've done all of these syntheses before. This one, we kind of talked about it just briefly in the aldehydes and ketones chapter, and this was hydrolysis of nitriles. Okay, and in case of hydrolysis of nitriles, you took an aldehyde or a ketone, you treated that with HCN, and you got a nucleophilic addition reaction, which if you treat with acidic water, then you will do hydrolysis on the nitrile group, okay, to give you carboxylic acid. Now, you don't have to do this just on a carbonyl. This is just a review for you. This is where you saw it before, but you can take any kind of an alkyl halide, do an SN2 reaction on that with the nitrile, actually with the cyano group, get a nitrile, and then do hydrolysis on that, okay, to get an acid. So if you want a diacid, you can do two substitutions on that, okay? And so this is a very good way of making carboxylic acids. And this is the reason why nitriles are actually part of carboxylic acid functional group, because they can be converted into carboxylic acid. This is a new one for you, and this is from Grignard reactions, and we have not done this one before. You know about Grignard reactions, okay, but you don't know about this synthesis. We talk about it only now because this is a synthesis of carboxylic acid. So if you take any Grignard reagent, okay, so again, remember, you will take butyl chloride, treat that with magnesium to get the Grignard reagent, and you take this alkyl group, okay, or this Grignard reagent, and you add carbon dioxide, and then you treat that with water, you will end up getting a carboxylic acid, okay? The one thing you have to remember for Grignard reagents, and also for the cyano compounds that we just did, is that when you make these compounds, you add one carbon, okay? So that's one thing to keep in mind. When you were doing the oxidations using aldehydes and ketones or alcohols, you did not add any carbon. But with nitriles and with Grignard reagents, you end up adding one carbon. So in the cyano, it's coming from the cyanide group, and here it's coming from the carbon dioxide. So when you use your starting material, it should always be one carbon less, okay, from whatever you are trying to make. You can use you can make benzoic acid also using bromobenzene, treating that with magnesium and making the Grignard reagent and so on. Okay, so it's a very nice little neat reaction to do. Regarding the reactions of carboxylic acids, there are few reactions, okay, they're all critical reactions of carboxylic acids. The acid-base reaction you've already done in the intro. We talked about that in the previous lecture. So that's how you do acid-base reaction. This is what is shown over here, the deprotonation. That is actually an acid-base reaction. You can also have nucleophilic additions, just like any other carbonyl. So all in aldehydes and ketones, we were doing nucleophilic addition. So this is like a nucleophilic addition here. And remember, when you do a nucleophilic addition, the carbonyl will give you an alcohol. Okay, I should say the carbonyl will give you an alcohol. Okay, and then things will add on to this carbon. In certain conditions, you can also have substitution going on, all right? So which means that OH now is going to be the leaving group, okay? And so once it leaves, you have whatever you're trying to substitute over here. Now, remember, OH is not the best leaving group, all right? So there are only very few reactions that you can do for substitution over here. The last reaction that we talk about in carboxylic acids is the one on alpha carbon. Alpha carbon is the carbon next to the carbonyl carbon. We'll have the same thing in aldehydes and ketones also. I kind of didn't mention it to you before because we have to do a whole chapter on it, but this is kind of shown here, so I will talk about it. The carbon next to the carbonyl carbon is called the alpha carbon, and so you can also have reactions on that. So whatever carbonyl compound you have, whether it's aldehyde, ketones, carboxylic acids, or esters, you will see alpha carbon chemistry, okay? And we will do that later on. So these are the 4 reactions possible for carboxylic acid. So let's see some specific ones. So let's talk about the reactions of carboxylic acid. We'll start with acyl chlorides. And acid chlorides are made, or acyl chlorides are made from the acid, and you treat that with thionyl chloride, or you can also treat it with PCl5 or PCl3, phosphorus pentachloride or trichloride. It will give you the same product, which is an acyl chloride. So this is butanol chloride. We will talk about this reaction again in the next topic as well. This is conversion of one functional group, one derivative of a functional group into another derivative of the same functional group. Okay, so we're going from an acid to an acyl chloride. And this is a very common reaction that we do for carboxylic acids because carboxylic acids are usually very stable and not very reactive. They do very few reactions. So to make them more reactive and to actually do reactions on carboxylic acids, you have to convert them into chlorides. The chlorides are not very stable compounds, okay, as we will learn later on. So as soon as you make them, you should use them. Okay, so then let's talk about reduction. Reduction is where you have the substitution going on, or excuse me, the nucleophilic addition going on. This first one was a substitution. This one is the addition reaction going on. So in addition, remember, the carbonyl will change to the alcohol, okay, and then lithium aluminum hydride, a very strong reducing agent, is used over here. So you add the hydride to this carbon, and so you add on hydrogen and hydrogen, you use 2 hydrogens over here. Okay, and so then you end up getting an alcohol. Now typically this reaction is not done the way it's written right now. Usually what will be done is you take the carboxylic acid, convert it to an acyl chloride, and then reduce it. Okay, because lithium aluminum hydride is a very strong base, and you can have an acid base reaction. Okay, so it's really not very productive to do it this way. It's much better to use acyl chlorides and then reduce them. But anyhow, lithium aluminum hydride is a very powerful reducing agent, which means it takes it all the way from acid to the alcohol. If you want to make aldehyde from carboxylic acid, you can do that too, but you definitely have to start with an acyl chloride and then use a mild or a weak reducing agent like sodium borohydride, dival, one of those. So reaction esterification, and esterification is a reaction between carboxylic acid and alcohol. And this is one of those reactions that acids do. All you need is a little catalyst, okay, to push the reaction, which is sulfuric acid. It's a very neat little reaction that you can do. And you get esters, okay? And we've talked about esters and we talked about polymers like in polyesters, but anyhow, you need an alcohol and you need an acid, and you need a little catalyst and sometimes a little bit of heat, okay? And then you can reflux this, or you can, heat this for a while, and you will get an ester. This is a neat reaction to do, and it's very common, okay? Esterification is a very common reaction. We will talk about the mechanism of this reaction later on, okay? Some of the other mechanisms also we will talk about later. Right now, you just need to know what these reactions are. Decarboxylation is also another neat reaction. Of course, they're all neat reactions. But in any case, in decarboxylation, you're losing carbon dioxide. So here we have carboxylic acid. And when you do decarboxylation, which is really high heat, okay? And so when you heat this to like 300, 350 degrees centigrade, then you can lose the carbonyl, okay? Over here, CO2 is gone. and then you're left with an alkane. Now, this reaction is not very advisable because your compound may decompose before it decarboxylates. So one has to be really careful in choosing what kind of carboxylic acid they want to decarboxylate. And you also have to indicate that you're losing the carbon dioxide, because there are some other reactions you can also do with heating carboxylic acids, all right? So when you talk about heat and decarboxylation, it's like really high heat, okay, that you have to mention. But anyhow, so you can decarboxylate. Now you have to remember again that if you're trying to make an alkane, you start with 1 carbon higher. So if you have 5 carbons that you're starting with in your acid, you'll be left with 4 because one of the carbons is gone as carbon dioxide. This is kind of like the reverse of the Grignard reaction, if you can think of it that way. So here we are with the synthesis. So all the oxidation reactions that we've done, again, this is just a review. You've done them from organic 1, so you should know all the oxidation synthesis, hydrolysis of nitriles, carboxylation of using Grignard reagents, and then of course all the reactions that we just talked about. Don't worry about mechanism yet. We will get to mechanism in the next chapter or in the next section.